All right. So at in the last class, we implemented one interface, two. We implemented two interfaces. We implemented the iterator and the iterable interface. Today, we're going to look at how to make your own interface. And then we're going to look at a data structure called a stack, which you probably have seen in, I assume you saw stacks in okay. So we're going to implement a stack in the easiest possible way that you can do it in Java. Well, probably the second easiest possible way. And that's going to lead into implementing stacks in other different ways. How did you implement a stack in C? Did you use an array or did you use a linked structure? No one remembers.
We did both.
You did both? Okay, so you're going to do both again in Java. All right. Creating an interface. So if you want to make your own interface for some reason, then it looks the same as implementing your own class. But an interface is just a list of methods, so it's actually easier than making your own class. Now, you might wonder why you might want to make your own interface. And so you create your own interface when you have one or more classes that are possibly unrelated to one another, but you all want them to have a common method of some kind. Right? So here we're going to implement, you'll see an example of implementing an interface where you can print an object. Right? So objects that implement the interface have a print method where you can, that automatically prints the representation of the object to standard out. Everything in an interface is public. So interfaces are meant to describe the public interface of a class. Right? So everything in it is public. If you try to make anything inside the interface not public, the compiler will complain. Right? So either have no access modifiers in the interface, or every access modifier is public. Right? If you try to use private or protected, the compiler will not allow you to do so. So here is our interface called printable. It just represents objects that can be printed to standard output. Notice that the comment says it's not a particularly useful interface, but it's an example of a simple interface that's easy to understand. Right? So all you do is you change the word class, you change it to interface. Otherwise, things are the same. Right? You then add whatever methods you want your interface to have. Right? So in an interface, it's only the method declarations. Right? In other words, it's not the definitions. So there's no body to any of the methods. Our printable interface will have one method, right, called print. Right? It's public and it returns nothing. Right? It has no arguments. Notice that there's no body. Right? So it's just the declaration of the method followed by the semicolon. Right? No implementation. Now, you can easily modify any class that you have the source code to implement the printable interface. Right, so for example, I can take the point2 class and I can have it implement the printable interface. Right, so currently, our point2 class implements comparable. Right? Now, in Java, a class can implement as many interfaces as you want. So you just list the interfaces, separating them with commas. Right, so that declaration says point2 implements the comparable interface and the printable interface. If it implements the printable interface, it has to provide the print method. Right? So you add your print method, right? And what does it do? Well, it just uses system.out.println to print the thing, right? Which is why it's not very useful. You could do this without an interface, right? You can always print out a Java object using system.out.print. Right? But there's an example of how you could create an interface and then have a class that implements the interface. Right? And so we're going to come back to this idea, probably not this lecture, but probably in the next lecture. Right? So keep the idea of interfaces in mind. We're now going to talk about stacks. So I can go through this pretty quickly because you've all seen stacks already. Right? So these are all examples of stacks. Right? So you should know, hopefully, your data structures instructor told you that anything you do at a stack only happens at the top of the stack. Right? So you can remove the element at the top of the stack. You can add an element on top of the stack. Right? So I can put another book on top of this stack if I wanted to. Right? And so classically, stacks only support two operations. There's push, right, which adds to the top of the stack, and there's pop, which removes from the top of the stack. Classically, those are the names of the operations, but there are other names for push and pop. But classically, these are the two names. So hopefully these are the ones that you were taught as well. Right, if you try to pop an empty stack, then in Java, the appropriate thing to do is to throw an exception. Right? In C, you have to choose how you want to deal with the error condition. Right? But in Java, throw an exception if someone tries to pop an empty stack. Right? You almost certainly would have seen a picture like this before. I'm just going to quickly go through it. Right? So if I have a stack of strings and I push 5 elements onto the stack, right, your stack ends up looking like this. Right? So the top of the stack just moves up as you add elements on top of the stack. Right? When you pop, popping will remove the element from the top. So it's going to remove the E and return that back to the caller. Right? And then it'll move the top of the stack down by 1. Right? So popping a stack, it just looks like this. Right? Until you get to the empty stack. So when I get to the stack of size 1, I can pop one more time and I have an empty stack, at which point you can no longer pop the stack. Right? If you write st.pop, you should get an exception now. Okay, so where are these things used? Were you told where they were used? Or were you just told this is a stack? You were told where they're used? Okay. So the most common place that people, the thing where you would have seen it, where a stack would have been used, that you've probably actually used on your computer, is when you do undo or redo. So in any computer in most computer programs that have undo and redo, the way undo and redo works is there's some representation of a command, right? So when you do some command, like type something into your word processor, right? Some representation of that command gets pushed onto the undo stack, right? You do something else, then the next command gets pushed onto the undo stack, right? If you want to undo the previous command, you pop the undo stack, and then you undo the command that comes off. Right? And then that command gets pushed onto the redo stack. Right? So if you redo something, then you pop the redo stack, you redo the command, and then put it back onto the undo stack. So undo redo is typically implemented using a pair of stacks. Right? And there's lots of other applications for stacks as well. Right? In particular, they show up in a lot of algorithms, especially when you try to do things on recursive structures like trees. And there's other places as well. Did they show you how to convert a recursive method to a non-recursive method with a stack? No? Yes, no? Okay. So did they show you recursion? They did, right? Okay. So if you have a recursive method or a function that you want to convert to the non-recursive version, one way to do it is to use a stack. Right? So there's a trick that you can play. Not a trick. There's essentially what you end up doing is you end up simulating how functions or methods work on your computer manually. And I think I'm going to show you an example of that either later today or in the next lecture. So if you want to reverse a sequence, you can use a stack, right? So don't do it this way, but you could use one. I'm going to show you the picture first, and then we'll come back to the algorithm. Right? So if I want to reverse that list T, right, then one way to do it is to use a stack. Right? So the way you do it is you take the elements of the list, and you just push them onto a stack. Right? So I push the A onto the stack, I push the B onto the stack, I push the C onto the stack. Right? You should know that a stack is a first in, last out. Right? Last in, first out. So LIFO data structure. Right? So the last thing you push onto the stack, that's the first thing that comes out. Right? So when you pop the stack, the C comes out first. Right? So if I take that C and I put that into the resulting list, right, that effectively reverses the list. Right? Now, you shouldn't do this because this particular algorithm ends up taking up, how much memory do you need for this algorithm to run? You need 2 times the size of the list. Right? I need memory for the stack, right? And then I need memory for the resulting list. Whereas you could just reverse the list directly, right? By going looping over the list backwards and putting the elements directly into the result. Right? So the method, if you wanted to use a stack, looks like this. Right? So I want to reverse a stack. I want to reverse a list T without changing T. Right? I want to return the reversed list as a new list. Right? So we make a new list. Right? If you're going to use a stack, you make a new stack. Right? And you simply push every element from T onto the stack. Right? So for each string S in T, push the string S onto the stack. Right? And now pop the stack until it's empty. right? So while the stack is not empty, right, pop the stack, take the element, add it to the result, right? And that gives you a reversed list. So a stack actually looks a lot like a list, right? So if you look at this picture here of that stack, right, if you sort of turn it 90 degrees to the right or 90 degrees clockwise, right, then it looks exactly the same as that list there. So pushing an element onto the top of the stack looks exactly like adding an element to the end of a list, right? Popping an element from the top of the stack looks exactly like removing the last element from the end of the list. So in Java, one way to implement this stack is to just use a list, right? So if I want to make a stack class, right, then internally, I can just represent, I can hold the elements using a list, right? So I'm going to use an array list in this case, right? And the field, I'm just going to call it stack, right? Elem or elements or something probably would have been better. But anyway, it's called stack, right? We need a constructor. Right? What does a constructor do? It initializes the field. So our constructor simply makes an empty array list, right, which gives us an empty stack. We've decided to add a size method so that someone can find out how many elements are on the stack, right? How many elements are on the stack? Well, it's just the number of elements in that list, right? So you just return this.stack.size. Right? Pushing an element onto the stack is equivalent to adding an element to the end of that list. Right? So to push that element onto the stack, you just add the element to the end of the list. Right? Now that's an array-based list. So adding an element to the end of an array-based list is usually has complexity big O1. Right? In a few lectures, you're going to see, though, that that's not always true. So occasionally, adding an element to the end of an array-based list has complexity big O of n. Right? And you'll see why when we actually implement the list. Pop is equivalent to removing an element from the end of the list, right? So I want to remove the last element of that list, right? I need the index of the last element. That's just this size minus 1, right? Now use the remove method. That removes the element from the list and returns it back to the caller, right? So now we return elem back to the caller, and that's it, right? You're done your stack implementation in about 2 minutes, right, or less, right? It takes very little time to implement the stack if you have an existing list class. Right? This stack can grow to any size, right? Because the list, right, the internal list takes care of allocating and deallocating memory for you, right? So if the list needs to grow, it automatically allocates a new array, copies the elements from the old array into the new array, and carries on. Right? So it's very nice. So having this list data structure in Java is, it's really nice to have, especially if you're coming from a language like C, right, where you're taking care of all your memory management on your own. That's not the only way to implement a stack, right? So you saw that you can also use some sort of linked structure, right? So a linked list-like structure to implement a stack, right? I can use an array rather than an array list to hold the stack, right? There are other ways to implement a stack as well, right? So there's many ways to implement a stack. They all have their own disadvantages and advantages. So for example, if you use an array compared to an array list, an array uses slightly less memory than an array list, runs very, very, very slightly faster, right? The disadvantage is, though, if you want to grow the array, you have to manually do it yourself, right? If you use a linked structure, using a linked structure usually occupies more memory than using an array or an array-based list, right? But if you use a linked structure, you can guarantee that push is always in O1, right? Which you can't guarantee with a list or an array-based list. An array, right? Occasionally, push for an array or array-based list is in ON. Oops, sorry. Right? So there you have several possible different implementations, each with their own advantages and disadvantages. Right? As someone who might be implementing a stack or someone who might be creating a library of some kind, right? You can actually provide all three implementations and let the user pick what implementation they want to use. Right? Now you want all your stacks to have the same interface, right? So you want them to be interchangeable. So someone can use an array-based list Or they can use an array list-based list, or they can use a linked list-based list. Array. Someone can use an array-based stack, a list-based stack, or a linked structure-based stack, right? And they should be able to use them interchangeably, right? So the way you do that in Java is you define an interface for the stack, for all stacks, right? And then you provide separate classes for the different implementations, right? And now users can pick which implementation they want to use that's most appropriate for their purpose, right? So the Java standard library provides you with an array-based list and a linked list, right? You get to choose which one you want to use, right? It provides you with many types of sets and many types of maps, right? All having their own advantages and disadvantages, right? The user gets to pick which one they want to use, and they're all interchangeable, right? So that's the power of using interfaces. All right, so we want to look at implementing. Is this the right one? Yeah. So now we want to look at how to implement a stack in a few different ways, right? And how to make an interface so that all of our stack implementations are interchangeable. Right. First thing I want to do is I want to show you how you can convert a recursive method into a non-recursive method. Right. Now, to understand how this works, you actually need to understand a little bit about how languages like C and Java, what happens when you actually call a function or a method. Right. So here's a little method that computes 10 to the power n. Right. This only works for positive values. Right? You can easily change it to work for negative values, but this only works for positive values. Right? It's recursive, which is dumb. You would never do it this way, right? But here's a recursive method that does it. Right? So recursive method, you've got a base case. Right? So if n is 0, the result is 1. Right? That's 10 to the 0. Right? Otherwise, right, if n is any integer value larger than 0, you just compute 10 to the power n minus 1 recursively. Right? Take the result and multiply it by 10, right? And that gives you 10 to the n. Right? So you can easily write a recursive method that computes 10 to the power n, and it's not an unusual method or an unusual function to ask a student to implement the first time that they see recursion. Right? It's also not a good method to implement recursively, right? Because there's much better ways to do this. However, this is what happens when you call a recursive method, right? So I'm going to call that method with the value 3, right? So in other words, I want to compute the value 1,000, right? So when you call that method, what happens in Java or C, right? So when you call a C function, the function runs in its own little chunk of memory, right? So in other words, when I call that method, power of 10, right? Somewhere in memory, a little chunk of memory gets allocated where the power of 10 method can run, right? The memory that's allocated, there's information that's stored here, right? So for example, right, that power of 10 method has a parameter called n, right? So that parameter n, that gets copied into or space is made for it in the chunk of memory where the function runs, where the method runs, right? The variable result, space is allocated for that variable inside the method, right? If there's any other local variables, space is also allocated for those local variables. Right? So there you can see that space is allocated for n, and space is allocated for result, right? There's other stuff that's allocated, right? So there's a bunch of bookkeeping stuff that's here, that's also allocated in this memory, right? But that's beyond the scope of what we need to talk about right now, right? Okay, so what does this method do? Right? So the method starts running. The base case is not true, right? Or the base case does not occur because n is not 0. Right? And so the line that happens is result equals 10 times power of 10 2. Right? So in other words, it recursively calls itself. Right? So that's what happens. Right? Now, what happens when it recursively calls itself? A separate version of power of 10 runs. Right? So somewhere in memory, a new chunk of memory gets carved out for the second version of power of 10 to run, right? The parameter 2 gets copied into that memory, right? And then the method runs, right? So the result, that's not the base case, so the result is computed as 10 times power of 10, 1, right? So there's another instance of a method that runs, right? When this method runs, right, that's not a base case, so it calls itself recursively, so another chunk of memory gets carved out, and a fourth version of power of 10 now starts running, right? Okay, now we've reached a base case, right? So we've got the case 0, so we know what the answer is for result, right? The answer for result is 1, right? And now the fourth version of the method can finish running, right? And it returns its result 1 back to the caller, right? So that 1 gets copied and replaces power of 10, 0, right? So that method finishes running, returns its result, and then it goes away, right? So the memory allocated for that memory disappears, right? This is an upside down stack that I'm drawing, right? Every time you call the method, right, a version of that method gets pushed onto what's called the call stack, right? So when I call that the first time, let me back up, right? So when I call it the first time, right, that's the top of the call stack. When it calls itself, that becomes the top of the call stack. When it calls itself, that becomes the top of the call stack. When it calls itself, that becomes the top of the call stack, right? So the way that functions and methods are implemented in Java and C, sorry, in C and Java, right, there's literally a call stack, right? There's a stack that's running somewhere, right? It may not, the representation may not be the same as what I've shown you, but there's a stack, right? When a method finishes running, right, it returns its value back to the caller, and then it gets popped off the stack, right? Now that I have a result, I can pass that value back to the caller, and then pop that instance of power of 10. Right? So that disappears, and that becomes 100, right? Now the 100 gets passed back up, right? And I can pop the stack, right? And now I'm done, right? So I now have the result, so I can return that value back to the caller, and I can pop the stack, right? So that's what happens when you actually run a recursive method, right? So if you have a recursive method and you want to convert it to a non-recursive method, then the trick is you emulate what the compiler or what the runtime system is doing for you, right? So in other words, you implement the call stack yourself manually. Right? So you want to simulate what the virtual machine is doing in the recursive method. The basic idea is you push some information onto a stack to remember what needs to be done when the recursive method returns. Right? So in power of 10, what needs to be done when each recursive call returns? Right? So when the recursive method returns, what do? Well, you just go and look at the, you just go back and look at the source code for the function, for the method. Where it is go to. Oops, sorry, I don't want that. Right, so if we go back and look at the implementation of the method, right? So when that returns, right, what do? You take that result and you multiply it by 10, right? And you store that in the result. Right, so I'm going to multiply the return value of the recursive call by 10. Right? So each recursive call that's not a base case pushes a 10 onto the stack. Right? So what I'm going to do is I'm going to use the stack to remember what is it that I need to do after every method returns. Right? During each recursive call, what happens to the value of n? Right? So remember, n is the value that we're passing in to the method every time. Right? It's a recursive method. Right? Our base case is that n is 0. Right? N starts out as some positive value. So n has to decrease every time by 1. Right? So each recursive call results in n going down by 1 every time. Right? All right, so what does our non-recursive version of the method look like if we use a stack to implement it? Right? So you start out with a stack. Right? It's going to be a stack of integer. So all I'm going to do is I'm going to record the number of 10s that I'm multiplying together. So that's all that's going to happen here. Right? While n is greater than 0, right? So this is going to simulate calling the method n times. Right? What do? You push a 10 onto the stack, right? To remember that I need to multiply the final result by 10. Right? And then I decrease n by 1. Right? So that simulates calling the recursive method with n minus 1 each time. Right? When this is done, you've got n tens on that stack, right? So how do you compute, right? A recursive call reaches the, okay, that's fine, right? Basically, okay, so how do I compute the final result, right? Well, the recursive call that reaches the base case results in a 1, right? So I'm going to start with the recursive case 1 and then multiply it by every 10 that's on the stack. Right? So my result is 1, and now pop the stack until it's empty, multiplying the values as you go. Right? So this simulates the returning of this simulates the return value of every method, right? So when you return from a method, you take the result and multiply it by 10. Right? So I'm going to start with 1, right? I'm going to pop the stack, multiply the result by 10, right? Because that's what's on the stack. Right? And I'm going to do that until the stack is empty. Right? And so that ends up multiplying 10 n times in a very convoluted way. Right? So it's an extremely convoluted way. But that's simulating what actually is happening when you write the recursive method, right? Or when you run the recursive method. So if you have a much more complicated recursive method than this one, right? The trick is to simulate the calling and unwinding of the call stack, right? So whatever information you need to remember between calls, right? You push onto the stack, right? And then you push the stuff off the stack and do something with the information that's stored on the stack to compute the final result, right? And you can actually simulate any recursive method in this way, right? What you end up pushing onto the stack becomes very complicated, but in principle you can do it, right? Now the reason you want to convert your recursive methods into non-recursive methods, right? This picture should also make obvious, right? Because every time you make a recursive call, right, that recursive call needs memory to run in, right? So if you're trying to solve a very large problem, right, where you have to make a recursive call many times, right, each call to the function eats up some memory, right? If the problem is very large, you can eat up all the memory that's available to you on the call stack. Right, so the call stack doesn't have as much memory as your computer has. The call stack on your, in most languages has a limited size. Right, so if you try to solve a very large recursive problem, often what happens is your program stops running and it says it's out of memory of some kind. You get some sort of out of memory error. Right, and it's because you're eating up all the space on the call stack. Right, so if that's the situation you're in, you have to take your recursive method and convert it to a non-recursive form. Right? One of the ways to do that is to use a stack. Okay, so using a stack in that example, that's way too complicated for actually computing 10 to the power n, right? But it illustrates the basic idea of using a stack to convert a recursive method to an iterative one. All right, so let's go back to implementing stacks, right? So if I want to implement a stack using an array, right, I have to do all of the bookkeeping that the ArrayList did for me, right, when I implemented it with an ArrayList. Right, so I want to take that list, I want to get rid of the list, I want to replace it with an array. Right? Problem number one that you run into is that the array always holds a fixed number of elements. Right? So I make an array of size 10, I can only put 10 elements into that array. Right? If I need space for more elements on the stack, I need to reallocate a new array, copy in the existing elements into the new array. Right? The ArrayList does all of that for you. Right? Also, if I have an array of length 10, but I have a stack of size 1, right, I only have one element on the stack. Right? So I need some way to remember that I only have one element on the stack, and I need to know where is that element in the array. Right? So I need a field to keep track of where the elements are actually stored in this array. Right? So instead of adding and removing from the end of the array, right, I need to keep track of which element of the array represents the current top of the stack. Right? So this is what my int stack is going to look like. So I'm going to make a stack that can hold ints, right, and only ints. Right? In a couple of weeks, we'll see how to make a stack that can hold anything. Right? But for now, I want to make a stack that can hold ints. I'm going to use an array to store the elements. Right? So I have an array field whose type is, I have a field called ARR, whose type is array of int. Right? And then I've got a field called top index. So that represents the index into the array where the top element is currently sitting. Right? If there is no top element, then top index is -1. Right? So in other words, it's an invalid index if there's no elements on the stack. Right? The default capacity, that's just the starting size of the array. The no argument constructor makes an empty stack. Right? So what do you need to do? I need to initialize these fields. Right? So I initialize the array so that it has its default capacity, right? Size 16 in this case. Right? I set the top index to -1, which indicates that there are no elements on the stack. Right? So notice I'm not keeping track of the size explicitly. Right? I'm using the index, the top index field, to keep track of the number of elements. Right? So that's what your stack looks like. Right? So that's a snapshot of what your array and your fields look like when you make an empty stack with this implementation. Right? So I've got an array of size 16. Right? It's a new array. So in Java, that gets set to zeros for you. Right? The top index is set to -1, right? Indicating that there is no element in the stack. Right? When you push a value onto the stack, what do? Right? So if I push a 1 onto the stack, for example, I want to replace the first element in the array with a 1. Right? How do I do that? I take top index, add 1 to it, so that gives me 0. Right? And then I set the array element at top index. Right? So increment top index, set the value at index top index. Right? Pretty easy. So here we go. Right? So I'm going to push a 7 onto the stack. Right? Top index becomes 0. Right? And then I set the array at index 0 to the 7. Right? If you push a -5 onto the stack, right, top index becomes 1. Right? And then you set the element at index 1 of the array. Right? What happens when you pop a value from the stack? Right? So you get the value at top index. Right? You then decrease the value of top index, right? Because you're going to remove that element from the stack, and you return the value. Right? Notice that you don't need to modify the value stored in the array. Right? So I don't have to erase or replace the value that was previously stored in the array. Right? So for example, I'm going to pop the stack. Right? Now I had a stack that had a 7 and a -5 on it. Right? When I pop the stack, right, I remember the -5. Right? I decrement top index, so it's now 0. Right? So the top of the stack is now points at element 0. Right? And then I return the value that was popped. Right? So we return the value -5 back to the caller. You don't have to overwrite that -5 with anything. Right? Because when I push an element back onto the stack, I'm just going to overwrite that value anyway. Right? So there's no point in erasing or replacing that value with anything. Right? So what does pop look like? Pop's easy. Right? Is the stack empty? Right? How do I know the stack is empty? I look at the top index. Right? So if the top index is -1, throw an exception. Right? Get the element at the top of the stack using top index. Right? So that's just the array value at top index. Right? Adjust the top of the stack so that it moves down or moves to the left. Right? And then return the element that was at the old top index value. Okay, so this is the state of the stack when you can safely do one more push. Right? So if I have my current capacity is 16. Right? So if I have 15 elements in the stack, right, then I can safely push one more time. Right? So when you push one more time, so when do I know that I can safely push one more time? Right? Or when I can safely push another element onto the stack? Right? When the top index, right, is less than the size of the array -1. Right? So notice that 14 is less than the size of the array. Right? So I can safely, when the top index is, that's right, when the top index is less than the size of the array -1. Right? So if the top index is less than the array length -1, I don't have to do anything. Right? I simply increment the top index, and then put the element into the array. Right? Now, what happens when you're out of capacity? Right? So if you run out of capacity in the current array, you need to add capacity by doing the following. Right? So you need to make a new array having greater capacity. Right? So in C, you would have done another malloc or a realloc. Right? Did you make variable-sized stacks, or did you do fixed-size stacks? You remember? Okay, so this might be new to you then. All right, so if you want your stack to grow to arbitrary size, right, you have to expand the size of the array. Right? So if you filled up that element, right, and I want to add another element, right, then your solution in this case is to make a new array. Right? Copy all the elements from the old array into the new array, and then make this ARR point to the new array. Right? So here, back here. Right? So what I need to do is I need to make an array with greater capacity. You need to decide how much bigger are you going to make the new array. I want to copy the old array into the new array. Right? Set your field to refer to the new array, and then you can push the element onto the stack. Right? So how much more capacity should you add? Right? So it turns out, so if you add one more element, if you add 1 to the capacity every time, that's the worst thing that you can do. Right? So if my array is full, and I reallocate a new array with exactly 1 more spot to hold the new element, right? What that entails doing is you have to copy all the old elements into the new array, right? And then add the old element, right? So that's big O of n, right? If you then push another element onto the stack, what do you have to do? Well, I now have to reallocate a new array, right? That's 1 bigger, copy the old array into the new array, right? And then push the element onto the stack, right? That's O of n again. Right, so if you choose to add a fixed number of values, if you choose to increase the capacity by a fixed number of values, that causes your stack implementation to become big O of n for the push operation. Right? It always takes big O of n time when you resize the array. Right? And that's no good. Right? So what you want is you want it to be big O of 1 most of the time. Right? And so the way to do that is you increase the capacity by some factor of the current capacity. Right? So for example, you can double the capacity every time. Right? So as long as you increase the capacity by a factor that's bigger than 1, that actually, you can prove mathematically that that guarantees big O, on average, that guarantees big O 1 time. Right? Every time you have to resize, it's big O of n, right? Because you need to copy the existing elements into the new array. Right? But on average, you can show that it's big O of 1. Right? So, if I have space, right, then it's easy to push an element onto the stack. If I don't have space, right, now reallocate a new array. Right? So make a new array. It's double the previous capacity. I've chosen 2. I think the ArrayList implementation in Java uses 1.5 for the factor. So I'm going to double the length of the existing array. I'm going to copy all the old elements from the, I'm going to copy all the elements from the existing array into the new array. So I'm going to use a loop. Right? I'm going to adjust my field so that it points to the new array. Right? And then I'm going to recursively push the element onto the stack. Right? This is recursive now, right? Notice, right? So the push method is calling itself. But that's fine, because when the push method calls itself, right, it's going to have sufficient capacity, so the base case happens. Right? If you wanted to, you could repeat these 2 lines here instead of calling the method recursively. Right? But you need to add the element to the end of the stack. Right? And so there's how you resize an array in Java. Right? It's a little bit easier than doing it in C. Right? In C, you would have to use realloc. And then memcopy to copy the elements into the new array. Right. Okay, So when working with arrays, it's a common operation that you have to make a larger array when you run out of capacity in the existing array, right? It's so common that the people who made the standard library gave you a method to expand the size of the array for you, right? So if you use arrays copy of, that will create and copy an existing array for you, right? So all of this code here can be replaced with one line of code here, right? Which is a lot easier, right? So if you need to make a copy of an existing array and you want it to have bigger capacity, right? Use copy of to copy that array, right, into a new array having that capacity, right? So the length times 2, right? So double the capacity, and that gives you the new array, does the copying for you, right? Saves you a bunch of work, right? And then go ahead and set your field to point to the new array, and then push the element onto the stack, right? And so there's the array-based implementation of a stack, right, where the size of the stack is not fixed, right? Not fixed. I'm going to stop there instead of going to the linked list-based stack. So we'll look at the third implementation of a stack in the next lecture next week, I guess. And so we'll pick up things next week. Any questions? Alrighty. Have a good weekend. Have a good